Welcome back, everyone, to our continued discussion of the theory and intuition behind the hyperparameters used for random forests. In this lecture, we're going to be discussing bootstrapping or bootstrap samples and out-of-bag error. In bootstrap samples, what we're trying to answer is, do we allow for bootstrap sampling of each training subset of features? In out-of-bag error, we're answering the question, would we like to calculate OOB error during training? Let's begin by trying to answer the question, bootstrap samples, whether or not we're going to allow for bootstrap sampling for each training subset of features. To truly understand this, we first need to understand what bootstrapping means in general terms. Bootstrapping is just a term used to describe the process of random sampling with replacement. Let's see a quick example of bootstrapping given a set of letters. Given a set of 5 letters, A, B, C, D, E, we could do a random sampling with replacement, otherwise known as bootstrapping. For example, let's bootstrap 10 chosen samples from this set of 5 letters. That means I'm going to randomly select a letter from these 5. So for example, I could start off by selecting C, then I randomly choose A, randomly choose D, and you notice that I am allowed to choose the same letter more than one time. This is known as bootstrapping, allowing to have a replacement, so random sampling with replacement. Notice here, the only way I could select 10 instances from a set of 5 would be with allowing me to select the same letter twice. And this is the main idea behind bootstrapping, that you're randomly taking items from a set. Later on we'll see it's going to be rows from our data set, and we do allow for rows to be picked more than one time. So this is all bootstrapping is. It's random sampling with replacement. Now, recall when we're talking about random forests and how bootstrapping is part of that, when we do each split for a decision tree within a random forest, we are randomly selecting a subset of features. This random selection of those features helps create more diverse trees that are not correlated with each other. So, to visualize this, recall that when we're starting to choose a split on one of these trees in our random forest, here we have 5 features in our data set. We randomly selected a subset of those features to continue to decide how to actually perform that split. Now, what we could do is add bootstrapping into this. Bootstrapping allows us to further differentiate those trees, meaning we can also bootstrap a selection of rows for each split. And this actually results then in 2 randomized training components each time you're creating a decision tree. And upon each split, instead of also just selecting a subset of features, you're going to bootstrap rows of data. So again, to make it clear, previously we just showed you that on each decision tree, we already understand that when we're creating a split, we grab a random subset of features. What we're going to do now, though, is bootstrap rows of data along with that subset of features. So each time you're doing a split, not only do you only see a subset of features, but you also see only a subset of the data rows. Which means, if we imagine a much larger data set dealing with the same 5 features, but this time we have index values 0 through 6, each of these representing a single row, what we do is for each of these splits, we're going to select a subset of features, and then what we're also going to do is perform bootstrap sampling. Notice here that I bootstrap sampled the rows from my entire data set, and I'm going to be using this in order to train my decision tree, instead of using the entire data set, which is what we implied earlier. And you'll also notice here that the row 5 has actually been chosen twice, meaning we're doing random sampling with replacement. So why even do bootstrapping? Why not just pass in the entire data set? Well, bootstrapping can be set to false during training. Keep in mind in scikit-learn, it's true by default. The reason we use bootstrapping is to have yet another hyperparameter meant to reduce correlation between trees. Reducing correlation between those trees helps our model generalize better to data that it hasn't seen before. And since trees are then trained on different subsets of feature columns and data rows, we know that the trees we create throughout this random forest are going to be quite different than each other because they don't get to see the same set of features at each split, and we also know that each tree is not going to get to see every single data row if we set bootstrapping equal to true. This again helps differentiate the trees, and it makes sure that the trees are not highly correlated to each other. If we did have a set of highly correlated trees, then it wouldn't be very useful to keep adding trees to the model. With bootstrapping, we can continue to try to get even more information from our current training data. Now let's talk about out-of-bag error, which attempts to answer the question, would you like to calculate OOB error during training? And to understand out-of-bag error, we had to understand what bootstrapping meant in regards to our data. Now, when we talk about out-of-bag error, we're referring to bagging. Recall, to actually use a random forest, what we're going to end up doing is we're going to use bootstrapped data and then calculate a prediction based on the aggregated prediction of the trees. And what I mean by aggregated prediction of the trees is, for example, for classification, that's when we tallied up for the most voted Y class, class 0 or class 1, class 3, etc. For regression, the aggregated prediction was going to be the average of the predicted Y values, since it's a continuous label. So note here that there's two things that have to occur. We need to be using bootstrapped data, and we're also going to be performing an aggregated prediction. And that's where the term bagging comes from. B for bootstrap and AG for aggregated prediction. So what does this mean in order to calculate out-of-bag error? Well, if we performed bootstrapping when building out trees, this means that for certain trees, certain rows of data were not used for training. And if you have a large enough data set with enough rows, typically, just statistically, the sampling is going to lead to the fact that about approximately 1/3 of your data will not be used for the creation of or training of a particular tree. So what does that mean if you have some data that's left over unused? Let's go back to our visualization. Recall that in this particular example, we decided on a subset of features, and then we grabbed a bootstrapped sampling of the data rows. And that eventually allowed us to build out some sort of decision tree within our random forest. However, if we think back to this subset of bootstrapped rows, that means there's going to be some rows that were never used in order to train and create this decision tree. In this particular example, it's row 0, row 4, and row 6. That means this particular decision tree in our random forest using bootstrapped sampling has never seen row 0 or row 4 or row 6, which would mean it's actually good test data. We could actually calculate its error on this data that it's never seen before. So what we could do is grab the rows that were not used during the creation of this decision tree, 0, 4, and 6, and use those in order to calculate some sort of test metric. So again, these are known as the out-of-bag samples. They were not used for constructing some trees, and we could use these to get performance test metrics on trees that did not happen to use these data rows. So what we're going to do is grabbing this set of rows, that is the out-of-bag rows, what we could do is run those through the tree and then get our predicted Y hat value, compare it to the correct Y known label, and get some sort of out-of-bag error. Keep in mind, this is not going to be the same thing as the full test metric, because really we're only working with particular rows on particular decision trees, where those decision trees did not get a chance to see those rows during their creation because of bootstrap sampling. And bootstrap sampling, because we can randomly select with replacement, that means that certain rows have a chance of never actually being grabbed in that bootstrap sampling in order to create the decision tree, which leaves the fact that we have these so-called out-of-bag rows where we can calculate an out-of-bag error or out-of-bag score. Now we should note that out-of-bag score, just setting that equal to true or false, is technically a hyperparameter that doesn't really affect the training process. Instead, it is separated from bootstrapping, where out-of-bag score is an optional way of measuring performance. Essentially, an alternative to using a standard train test split methodology or cross-validation methodology, since bootstrapping naturally results in unused data during training. So whether or not you set OOB score equal to true or false while you're creating a random forest, that's not actually going to change the trees themselves. Setting bootstrapping equal to true or false will change the trees, but setting OOB score is just answering the question, would you like to keep track of that OOB error, yes or no? Either way, it doesn't actually change the decision tree itself. Choosing to bootstrap would change the decision trees. Now, because of that, we should note that OOB score is also limited to not being able to use all the trees in the random forest. Recall, because of bootstrapping, there are going to be some trees that end up using those OOB data rows that certain trees did not get to use. So that means that that out-of-bag score or out-of-bag error can only be calculated on trees that did not use that out-of-bag data, the rows that were not used during bootstrapping. Now, due to the fact that we actually don't use the entire random forest when calculating OOB score, instead, you're only going to do it for trees that didn't happen to see those out-of-bag data rows. That means we're not ending up using the entire random forest to calculate this performance metric. So, because of this limitation, the fact that it's not as robust as a full train test split where you get to use the entire random forest on data it's never seen before, in scikit-learn, the default parameter for calculating OOB score is set to false, which means if you were just to run the default settings for a random forest in scikit-learn, you would perform bootstrapping, allowing you to create more trees that were not correlated to each other, but the default is to not bother to calculate this out-of-bag score. But remember, you could set this OOB score equal to true, which would allow you to see how well certain trees are performing on data it did not get to be created with due to bootstrapping. It's just another piece of information that you could calculate if you want to. We now understand the theory and intuition behind random forests, as well as the specific hyperparameters that we can adjust, including how to choose the number of estimators, number of features to consider during a subset split, and we also now understand how bootstrapping works, which remember by default is set to true in scikit-learn when we're building out a random forest. And we also understand that if we happen to perform bootstrapping, that there are going to be some rows not used during the creation of some decision trees. And if we wanted to, we could then pass those unused rows into those same decision trees to get some sort of idea of how certain decision trees are performing on rows of data they've never seen before. Again, not as robust as a full train test split because we don't get the chance to use the entire random forest. Speaking of random forests, let's move on to actually exploring how to use random forests for classification and regression by coding it out ourselves. I'll see you at the next lecture.